Hello. Now we are going to think about another measure, the standard error of the regression, as an alternative measure to the goodness of fit. And let's go back to the population regression equation. We wrote the relationship between x and y in this way, and u is the error term, and it is purely a noise or an error. So it is random, and you can think about its standard deviation. By the way, the error term is always assumed to be mean zero, so expectedly zero. That's kind of the definition of error. So expectedly zero, but sometimes it could be negative, sometimes it could be positive. So the mean is not important for the error, but more important is the standard deviation. So the standard deviation of the error term is the average size of the noise in the true relationship, between test score and student-teacher ratio. So it's like you can interpret this as the effect of other unknown components, like in the determination of test score, there must be a lot of factors other than student-teacher ratio, right? So all of them are observed into U in this equation. Everything is included in U. So the standard deviation of U captures how big those unobserved factors effects are on Y. So then, on the other hand, you may do the same thing for the estimated regression equation. So again, the realization can be written as predicted part, this much is predicted, and this is the prediction error, residual. So residual is so then if you also, again, I told you that the mean of the residual is also zero. So its mean is not a problem at all, but its standard deviation is a concern. We are going to study that. So the standard deviation of the residual can be interpreted as the average size of the prediction error, right? Prediction error can occur because of those unobserved factors. And anyhow, the standard deviation of U hat is referred to as the standard error of the regression. So this is the most important noise or like most important thing when you measure the prediction, how well you are predicting Y. So then it's easy to understand why we need to calculate this. So the standard error of the regression is basically the standard deviation of the residual you had. So if you remove the radical, then you get summation of something squared, and inside the square, inside the parentheses, you have residual minus its mean, its sample mean. But we learned the sample mean is always zero, so it does not matter. You can just drop that. Anyhow, this is the difference between the realization and the mean, and square that and sum that and divide that by n minus 2. So wait a minute, why we use n minus 2 here? It's not n minus 1, but n minus 2. Very weird. So we'll explain that. And so inside the radical can be understood as a kind of variance of U hat. Exactly, this is almost so exactly the same as the sample variance formula that I introduced in the previous video, except for the denominator. The denominator is different, and so if you just take it for a while, take it as granted for a minute, then what does it mean? It's the unit of error. So average size of residual or average mistake by the OLS regression line, or and almost equivalent, almost the identical another measure is the root mean squared error. So it's the only difference is the denominator being n or n minus 2, but idea is same. So you had is the prediction error, you squared it, so squared error, and the squared errors are summed and divided by n. So summation and dividing by n, this is taking the mean. Exactly, this is the same operator as calculating the sample mean and take square root. So root mean squared error, and as in the end, actually that's almost the same as the standard error of the regression. So interpretation is the same, and the idea is the same. So just we would like to measure the size of the estimation error. And then why do we use n minus 2? Why do we use n minus 2? Then to explain that, it is useful to define the degree of freedom in statistics. In statistics, it is not a rigorous argument, but quite commonly used intuition in many textbooks and many classes. So let's think about this. When you calculate a measure from n number of observations, then the degrees of freedom is n. So you are using n observations, so we call that degree of freedom equals to n. And the examples are, for example, when you calculate, it should be x bar. When you calculate the sample mean, then you are going to get just like sum n observations and divide by n. Or if you calculate the probability of x smaller than 0, then what you are doing here is you are counting how many observations are smaller than 0 and divide that by n. So in those cases, in those two examples, simple examples, you have n degrees of freedom, because the degrees of freedom are coming from the data. However, when you calculate one measure like this, you consume 1 degree of freedom. So now let's think about the sample variance. You would like to calculate the sample variance from n number of observations. You have x1, x2 up to xn, and I would like to calculate the sample variance. If you remember how you calculated the sample variance, the first step is to calculate the sample mean, sample average first. And when you calculate the sample average, your degrees of freedom is n. However, after calculating the sample average, and if you use the sample average for the next step, then suddenly your degrees of freedom is n minus 1, because in the previous step you consumed 1 degree of freedom. Make sense? It may sound absurd, but this is just maybe the easiest way to understand why we use n minus 2. Later in the next chapter, we are going to generalize this idea to like n minus k when you have k parameters to be estimated. And in this case, but idea is simple enough. You have n observations, but one of them has been used to calculate the sample average. So when you calculate the actual variance, your degree of freedom becomes n minus 1. That is what you use in the denominator. You have to use that in the denominator. That's the sample variance. Otherwise, if you use n, then your estimator will be biased. You are underestimating the variance. Okay, then extending this idea to regression model, you are now when you calculate the standard error of the regression, you consumed 2 degrees of freedom because you had to calculate beta 0 and beta 1. Calculating U hat does not consume anything because it's just one-to-one. But when you combine data and estimate something, that will consume consume your degrees of freedom. So in calculating beta 0, you consume 1, and another in calculating beta 1. So you only have n-2 degrees of freedom when you calculate the standard error. It's very interesting. So as a result, if you use this n-2 formula, then your estimator is unbiased. Otherwise, if you use, for example, if you use n or n-1, then your estimator is biased, especially underestimating. However, but in the end, so when the sample size n is say 10, for example, then n-1 n is 10, n-1 is 9, n-2 is 8. So n and n-2 differs 20%. They are different by 20%, but when the sample size is 1 billion and 1, then n is 1 billion and 1, n-2 is 1 billion minus 1. So their difference is maybe like 1 out of 1 billion. So 1 over 1 billion is like 0.000001. So it doesn't matter in the end. Even if you have bias, that will be nearly negligible. And you are not going to read up to that much decimal place. So in practice, don't worry too much. But when needed, I recommend you to use n-2 based on this intuition. The intuition is strong enough. And I am going to go back to this slide in the next video. We are going to apply those measures to the estimation results we obtained earlier. Okay, see you later.